Okay, I'm recording the class. Please, if there is any objection or any problem with recording the class, let me know. And we can talk about that or even stop the recording if you have problem with that. All right. So no question from last week. Did you manage to get the book from Springer website? It's official, it's through university, and well, it's legal. Actually, you can log into Lady Library for Engineering, go to Springer weblog with your username and password. You get access to a set of books and resources. So this book is one of those, and that's a good thing about this book and this specific textbook. All right. Last week we talked about robots in general and different areas with robotic application and categories of applications as we had. If I just gain here, yeah. Applications in manipulators, in vehicles, in man and robot systems, and biologically. We had a brief review on those and concepts of robotic and applications. Now I want to just briefly look into industrial robot manipulators, those which we have most around us, and they probably have the most application seriously in industry with robots, and probably for some of you already who are working already in industry, this is something you see daily or you work with regularly. Okay. A manipulator robot normally is a closed loop control. Closed loop control, it's a keyword. It's a technical word. Conceptually, we say a system is closed loop when system has a controller which looks at result of the acts and based on those results makes decisions. So in a block diagram shape, if I have a system like this system can be anything, can be mechanical, can be chemical, can be any kind of system. So if I have a controller, for instance here, this controller controls the system, but to do so, it looks at the inputs. So you're applying a request move based on what you have at the output. Your controller makes decision and applies the new actuation or decision order to the system. Well, this is a topic will be discussed in a course called Control System in more details, but generally what we have in industrial robots is a closed loop. You have a feedback from what you're doing and what is your move in the output. This can be combination of human and machine or just machine. Normally they are programmable, so you program them for a specific sequence, pick something from point A, put it on point B, then do C, and so on and so forth, and you program that in the computer to in the controller of the robot to do that regularly as a sequence of operation. They are mostly multi-purpose. These robots are kind of general manipulators, so you can use them for different tasks. They are capable of different sets of tasks. Not every robot is capable of every job, but most of these robots are capable of several different types. And based on how do you program it, based on size, based on type of actuators you have, and the vectors you can connect, type of programs, they can be used for different applications. They're flexible or mobile. Normally, we want them to be flexible because having robots in manufacturing, in industry, is an investment, and you would prefer to have best result of your investment. You have spent money on some robots and you want to use them at different tasks flexibly. So normally they are flexible and mobile. You can move them if it's not, completely mobile, but it's also is possible to move them. It's not something that the stock somewhere you cannot move them. They're programmable in 3 or more degrees of freedom. I'll talk about that degree of freedom. What does it mean, and what is it? Okay, let's talk about degree of freedom. What is degree of freedom in a robot? Think about an object. So think about an object like this. If I bound this object, if I restrict this object to move only in one dimension like this, just a line back and forth. That's it. So like something, I restrict that item to just move left and right. That's 1 degree of movement. That's 1 degree of movement. Okay. Or another example, consider a pendulum like this. So you have a bar. On one side, there is a joint and it's fixed on one side. On the other side, it can move like that. Again, you have 1 degree of freedom. 1 degree of freedom. Did I have the message? I hope not. All right. Okay. For example, if I have a bundle like this, I've joined one side, it can move only like that. So it will be 1 degree of freedom. 1 degree of freedom. The number of degrees of freedom of a mass particle is defined as the number of independent variables necessary to complete description of the position of a mass particle. So in this case, if I know that my mass is restricted to move alongside a line, the only information I need to know is where is the origin? Like this. So if I know that my object, my particle, or whatever it is, can move only on this line, the only thing I need to know, where is it right now compared with the origin. So if here is the origin, I only need to know the position of the particle is x from origin. That's it. You don't need anything else, okay? Or in this case, well, you can consider like a reference angle or origin angle. And the only thing you need to know is, what is the angle right now? What is the theta angle of the particle? You don't need anything else. That's why we call it 1 degree of freedom. 1 degree of freedom. So if I have an object which can move on a plane like this, can go up and down, left and right, just it can move this way and this way, up and down, then by choosing a reference, an origin, to say where is your particle right now, you need to know how much is x, how much is y. We call that 2 degree of freedom. So think about that. We are talking about particles or objects, 3D objects, and these 3D objects can move on the wall, on space, on a 3D space or 1D space or 2D space at different positions, depending on how much information you need to provide to make it clear what is the position and what is the situation of the object or particle right now. That will be degree of freedom. For example, if instead of having one linked pendulum, you have two arm pendulum like this, in that case, you have two angles. Well, depending on how do you define it, okay? Depending on how do you define that, like this, okay? So I have theta 1, I have theta 2. To describe the position, to explain where is my object right now, I need to say what is theta 1 and what is theta 2. That would be 2 degrees of freedom. In a plane or in a two-dimensional plane like this, as I said before, to say where is my particle right now, I have to have an origin similar to what we had. And based on that origin, I can say, where is my particle, just by knowing that, well, this particle is x alongside x axis and y alongside y axis. That would be my degree of freedom. Degree of freedom. Now, considering physical movement, considering geometry of 3D objects, you can come up with variety of combinations of angle and distance together. For example, if you look at this figure on the right hand side, you see what you have here is you have one angle here, you have one angle here, so you have theta 1, theta 2, and also this distance is also variable. This length is also variable. So depending on how much is your x or l or whatever you call it, position of end point or the particle or the object will be described based on theta 1, theta 2, and L. Okay, this is a basic of finding location of an object in 3D space, But since we are talking about 3D objects, we are talking about robots, and also we try to formalize everything, make everything clear mathematically, because I need to write a program for my object. So think about that, what we have in our hand, for example. I hope everyone can see me properly. We do that automatically. I don't think how to move and how to grab an object by my hand. But for just 1 second, imagine that your hand is not automatically controlled directly by your brain. You have to program it. You have to control it by giving address, giving location of different objects. So if you want the hand, the robot hand, to go and grab something at the location, you have to tell it where is it, just in terms of distance, in terms of angle, in terms of position, all those details. That's our problem in robotic. In robotic, you're sitting in front of a panel, or you have a panel in your hand, and just by adjusting these length and angles, you try to reach a specific point and a specific position. Problem goes even deeper than this, because when I talk about a 3D object, normally what we do in algebra, in elementary math algebra, okay, when I talk about a 3D space like this, x, y, z, right? I describe the position of a point at this system. I would say, okay, there is an x, there is a y, there is a z or z for this position. So this position will be represented by, if it's position P, it's XP, YP, ZP. So this point will be described by XP, YP, and ZP. If you give me XP, YP, and ZP, and if I know where is the origin and the orientation of my of your coordinating system, if I have or we agree on coordination system, and you give me XP, YP, and ZP, that's enough to know where is point P, to find point P, to move my end effector, to move my arm to reach to point P. If you have complete agreement on that and you give me this information. But talking about 3D objects is not that easy. 3D objects might be slightly more complicated. So think about one object. If you know X, Y, and Z, this object has 3 degrees of freedom, can go to any position in 3D space. If you instead of one object, you have just 2 objects connected together, one of them is fixed, so this one is fixed, the other one can move. Okay, the other one can move on any direction. But the only problem is this distance is fixed. In that case, the second object is bounded with the distance to this point will cover a surface. What is the shape of the surface, you think? In this figure, if I have 2 particles, 2 objects connected with a fixed bar together, one of them is fixed, but the joint can go anywhere. So something like this. The other point can move around. What would be the shape of the surface it can scan?
A sphere.
I heard something. Sorry?
A sphere?
Sphere, yes, exactly. It covers in a sphere shape, okay? Covers in a sphere shape because this link between this point and this point, this link is fixed. So it can cover in a spherical shape like that. A surface which is spherical shape, a ball-shaped area. All right? And when you have 3 particles, 2 of them are fixed lengths, fixed length here. This is fixed, this is fixed, this is fixed, but these 2 are joined. So what I have are 2 points fixed and the end point only can move. So like 2 pens reaching to somewhere, at these 2 points here I have joints and the other one can move. That will cover a one-dimensional shape. Will be a circle. Why a circle? Because in this case, you have limited your movement only on one direction. It can go this way or this way. This is against, these 2 lengths fixed. If they're fixed, if the whole shape is fixed, it can go in that direction. So it will cover only a circle. So you see that when you have combination of objects, you have 3D objects, particles connected together. The way you connect them together, the way they can move, will make our math, our geometry slightly trickier compared with what we have. So we have to define other things as well. So, for example, just I'm using my cell phone. I hope everyone can see what I'm showing. By clicking on my when I'm talking, by clicking on my page, you can flip between me and the slides if you would like to switch between that. So if I have my cell phone in hand, I normally do that in class. I hope it works online as well. To tell you where is my cell phone exactly, or what is the situation, means position and orientation of my cell phone. I have X, Y, and Z to tell you where is my cell phone in 3D space. But it is important, and I also need to know that what is the orientation of my cell phone. See, my cell phone, one orientation and standard, or just original orientation can be like that. I can rotate it this way. I can rotate it this way, and I can rotate it this way. And it's true for all objects. So for any 3D objects, because we are not talking about points anymore. So if it's just a point, a dot, 3 information will be enough. So you have 3 degrees of freedom. If you have one point object, so just 1 point without any dimension, okay? But if you have an object, 3D object, this object is somewhere, I can say, where is the position of that object? So if it's not, a symmetrical object, something like a shape, it has a shape like that with a hole in it, something like this, yeah. The position of the object can be described by XP, YP, ZP. But also, you need to say what is the orientation of the object. What is the orientation of the object? So your object, depending, since it's a 3D object, you can define the orientations based on rotation. Okay, so you can say the orientation is like angle 0, 0, 0, angle 0, different numbers. So you have 3 for orientation and 3 for position. Overall will be 3 degrees of freedom for a 3D object, which is true for robot as well. A robot end effector, the end of the robot, it can be any kind of end effector, a gripper or anything. It also can have orientation, different kind of orientation. Look at my hand. I can move it up and down like that, turn it left and right, or rotate it like this, okay? That also will be included in my movement. So a rigid body has 6 degrees of freedom. 3 translational means linear, just for the position, and 3 rotation. So if I have an the asymmetric shape, I don't know, something like that, which is not symmetrical, okay? You also have to talk about orientation of the object. So the first 3 degrees of freedom describe the position of the body, and the other 3 degrees of freedom determine the orientation of the object, orientation of the particle or object we have. The term pose is used to include the position and orientation both together. So pose of the object. It is often said that while the world surrounding us is 3-dimensional, the world of robotics is 6-dimensional. Well, this is kind of considered as an irony. It's not exactly 6-dimensional, but you need 6 pieces of information to describe what is the situation, what is the location of the specific particle or robot at the current time. Any question so far? Any argument?
Yeah, I think 3-axis translation as well as 3-axis rotation constitute the 6 degree of freedom. Is it correct?
Say it again. 3-axis.
3-axis XYZ translation, and the same time the rotation of the 3-axis constitute the 6 degree of freedom. Is it the correct statement?
Yes, you can say that as well. Here we try to keep it as simple as it is, but yes, you also can define something like this.
Because in CAE, when we do analysis, so 6 degree of freedom, there we consider that 3 axis and 3 rotations, that rotation of XYZ axis, and total becomes a 6 degree of freedoms.
Yeah, 6 degree of freedom. You can relate that to your coordination system. Yes, you can say this is XYZ, and this also can rotate on this direction.
Yes.
This one can rotate in this direction. The other one can rotate in the other direction. So if I have 3D axis, like my hand right now, like this, I also can rotate this at different direction to have the right. But we normally use this because well, in algebra, in math, okay, in mathematics, we deal with points, with dots. We don't consider solid objects. Normally, we deal with just one point. We want to figure out what is the position of that point, and that's why we need X, Y, Z. For people who are working on pure math or students working with elementary math, it's kind of weird. 6 degree, what does it mean? We have only 3 degree. If you look at an point not as a point, as a solid object, in that case, you really need that. And if you care about not just position, the pose of the object and the orientation. I agree that that can be also related everything just to the coordination system instead of having, make it detailed, saying that I have XYZ right now and the orientation would be this. But you also that can be good for mathematical approach, but for robotic we would prefer to keep it as simple as we can, because later you remember that you need to write equations, write a program for this. So what you say is correct exactly, but we try to simplify for robotic level. I don't know. Did I answer you, or I agree with you? I hope I haven't made it more complicated.
Yeah, okay. I'm okay with that. Yeah.
Okay. All right, good. Very good. So any other question? Okay, very good. So let's now have a look at robot, at the structure of a simple type of robot. So in a robot structure, we can divide it into 3 basic parts, very basic part. One is the robot arm, one is robot wrist, the other one is robot gripper, or actually end effector of the robot endpoint. So arm of the robot is the part which actually lets you to have access to different locations in the workspace of the robot. So if your robot is supposed to work in a cage or in a workspace, work area, different points of that work area will be accessed by just changing or moving these arms. Wrist, well, it's better to say the end effector or gripper is the part which does the job for you. So you're moving your robot arm to grab something, or to do welding, or to do something else, okay, with the, or do painting with this. We call that an effector or gripper. And the connection between these two is your robot wrist. Similar, very, very similar to human or ape's arm, actually. What we have, several joints, the arm moving, and we have a wrist, which is normally flexible, can normally create 3D of freedom, so gives you different orientations, and the end effector to grab or to do something for us. So this is a basic definitions of robot. For those who are not familiar, for those who are familiar, you already have seen and know that. So position normally are determined by arm, and orientation is normally by wrist. Not exactly, but well, roughly. Position is mostly just controlled by arm, and orientation by the wrist. Robot arm provides the requested position of the gripper, and the robot wrist requires the orientation of the gripper. So before I move on, what we want to do is we want to have a look at different possibilities, different basic shapes, geometrical shape of the robot, how to connect. First, let's start with these joints. You are joining different links together, We call this is the link, and this is the joint. These joints. Let's have a look at joints and see how many different joints are possible for us. Two basic structures for joints, again inspired by what we see in nature around us, are rotational joints like this. So I have one link joined to another link, and it can rotate like this. So I have a joint and let it rotate. And the other one is translational. So rotational and translational joints. In the translational, what you have is one side can move alongside the other side, but linearly, not in terms of rotations. For example, again, if I have one link, the other link can move back and forth in parallel, or depending on the combination, it can be different angles, but the basic movement is kind of linear, back and forth. So my joint or my connection lets these two move against each other, okay? So this one, normally for rotational, we need to use motors, okay? For the other one also, we might need to use motors, but we need to convert rotational movement into linear with different kind of interface, mechanical interface devices to convert rotation to linear movement, or use pneumatic or hydraulic sources of movement to move back and forth. It can be for rotation also, we can use hydraulic or pneumatic, but different kind of actuators. For sensors as well, if I'm using rotational, I have to use sensors which can measure angle, theta. And for translational, I need sensors to measure d or distance. So these are details of different kind of joints of robot, So robot joints can be rotational or translational. Axes of neighboring joints, according to this, can be in parallel or perpendicular, which means that, so for example, if I have one robot moving like that, the other one, this one can move back and forth. So I can consider that this is X, Y, Z. This one might have a different kind of coordination system respective to the original one. I'll talk about this later in the next chapter, okay? So the axes of the neighboring joints can be in parallel or perpendicular to each other. By combining this rotational, translational, by joining different links, you can create different robot structures, like anthropomorphic means human-like kind of robots. Arm, which looks like human arm. Spherical, scatter, cylindrical, and Cartesian. I briefly look at those, and we go through different combinations just basically. Any question before I move on? All right. Anthropomorphic are kind of combination like you see in many industrial robots. We have this sort of robot arms in which we have rotation. We call it RRR joint. We call it RRR joint. So robot arm has 3 joints of rotational type, RRR, and workspace encompassing the points that can be reached by the robot endpoint has a spherical shape, like our arm. So if you look at your arm, if you stay somewhere, don't move, okay, the longest, the farthest area you can cover by your arm, see, the maximum is part of a spherical shape. Well, because we have, when you extend the robot arm to the maximum and you try to scan the whole area, it covers, if it's not a complete sphere, but it's a spherical surface. It is anthropomorphic kind of arm. Spherical arm, similar to the other one, but the instead of RRR, look at this, RRR, the last one is also moving, is RRT. So in that case, so you have a rotation like this. You see, this robot can rotate clockwise, counterclockwise here, and also can rotate here, and can extend back and forth the last piece of the arm. So it's RRT. The spherical robot arm has 2 rotational and 1 translational degree of freedom, which is that's why we call it RRT. The workspace has a spherical shape, similar to workspace is the largest area it can cover, so it's spherical shape. The other one is called SCADA, stands for Selective Complaint Actuated Robot for Assembly. It was invented, I don't exactly remember. It was invented, I think, by a Japanese company, if I'm correct. Its robot arm has 2 rotational and 1 translational joint, which is RRT again. So look at this. This is RRT, but look at the combination. You have rotation, and extending back and forth, and this one is rotation, this degree, and this one, and here is up and down. So this robot can move at different places and reach to ground, pick something, put it somewhere else. So it has many applications in industry, specifically for pick up and place robots. So by rotation at this joint and rotation at this joint and up and down, it can reach to different places. The workspace has a cylindrical shape, so be careful with that. So this one can cover a cylinder like that. So an area which can rotate and also up and down depending on the arm length. It might not be a complete, but part of a cylindrical space. And cylindrical arm is a robot with RTT joints. I have rotation. This one can go up and down, and this arm can go back and forth. So robot arm has 1 rotation and 2 translational joints. The workspace has cylindrical shape. Workspace has a cylindrical shape. Any question? So can anyone tell me, what do you think will be the difference between cylindrical arm and SCARA? Is there anything you can do with SCARA we cannot do with cylindrical, or vice versa?
Drill.
People with more experience have more responsibility now. Yeah, go ahead. Someone just said hello and didn't continue. Questions? Is there anything you can do with SCARA type of robot which you cannot do with spherical type of robot, or vice versa? Since cylindrical can raise the, sorry, I missed the comment. So Liu says seems cylindrical can raise the height. You mean it can go up and down? Would you like to come in and talk about that, Lou?
Yes, exactly. I think the cylindrical can move upward and downward, while the SCARA couldn't. I mean, on the second joint. I mean.
But SCARA also can move here up and down. So you're saying this is not enough here? You know, look at this. This one can move down and bring things up.
Yeah, but only to the certain level. But the cylindrical has the second translation can add extra height. You mean to extend further higher.
Mm-hmm.
I think SCARA has the double rotations.
Yes. So, but does it make a difference? Does it make a difference? Nikita also says weight that can be lifted is different. SCARA will have less power due to the design and speed. SCARA will be faster. So would you like to come in, Nikita, and say why you think so?
Basically, you're making a SCARA arm more flexible, having the two rotations, in compared to the other one, which has only one rotation flexibility, but it has a translation, double rotation, double translation.
Yeah, but Jason disagrees. Jason, do you want to discuss?
Can you hear me?
Yes.
Yes. Okay. Well, as far as speed goes, if you've got two different stroke lengths for height adjustment on the cylindrical, if I'm understanding that right, then they can both move rapidly.
Here, you're saying that it can move.
Faster.
Okay. All right. So you don't agree. You don't agree with the speed. One is faster compared to the other one. Am I right?
I'm saying, right. Yeah. I guess I was thinking there's two different stroke lengths on the lift in the height direction, but not. So I guess they'll be the same speed.
You can use one to put bolts or drill holes where the other one you can't, because it rotates around one. It actually doesn't go straight in the road.
Okay. Mike says SCARA is faster to pick and place. Mike, is it because of its design? You have pneumatic. You know that pneumatic actuators are normally well, it's hard to say because we have electrical, but pneumatic mostly are good and fast. You know, light, and you don't have motor to move. You just have a air pressure. Is it because of the design, or is because of type of actuators you are using, because these are different. Now we are talking about geometry. You know, imagine if we give you as much a piece of metal you need, just the links, and you have option to have two robots with the same weight, with the same type of actuators. So both are using same type of actuators. Would you say that one of them is faster than other one? Is it really the case? I know that in practice, well, something like this, very light. You see aluminum side, and I'm sure I think this arm is most likely pneumatic. It can just pop out, pop up, and very fast moving around compared with one with motor. But forget about the actuator. Think about the geometry. Think about the structure you have. Well, do you see any difference? I really would love to discuss that, to see, and also learn. Yeah, because I know that some of you are working with these devices daily, and you probably know that one of them is more, needs more maintenance. Some of them are faster in real work. Some of them might be noisier, stronger. Any idea? Okay, so the differences, probably one of the differences would be okay. Nikita, yes, to move scalar linearly, we need to actuate two actuators. When in cylindrical arm, we need to actuate only one. Linearly, what do you mean by linearly? You mean the pathway, right? The end effector pathway. You want to move it from here to here.
Yes.
Yeah, okay. That's actually one of the points which I'm trying to make. In terms of here, in terms of speed and those other things, we need to look into dynamic. Well, what does it mean, dynamic? If I want to move an arm like this, here I have to have a torque applied to this. I have to have torque applied to this joint, and I have to have a force applied to this joint. In the cylindrical, I have to have a torque applied to this. I have to have force applied to this and force applied to this. How do you produce those torque or sources? Really is important. Some cases, one might be easier than another one, or more suitable compared to the other one, depending on the weight, depending on the speed you're expecting, depending on many different things, just to make a decision between two type of robots which are similar, more or less together. The other point is, if for some reason, the pathway of movement is also important. For example, I want my robot to move along a path line, like in painting, like in welding, like in different reasons. Like I have an object here which I don't want to hit. I want to avoid. There is an obstacle in my workspace for some reason. Normally it doesn't happen, but for some reason, let's say, I have collaborative robots working together, and it is important this robot from point A to point B goes and never ever enters this area, because another robot is working and coming and going here, right? In that case, it might make difference, slight difference if you consider this moving pathway, and also the dynamic, as I said, the forces you're applying, the torque you're applying, the energy you're consuming when you have these robots working. Okay, so any other point you want to make or discuss? That's what I think. I would like to hear, what do you think? Agree, disagree?
Potentially, I think the cylindrical arm has more flexibility to go up and down. Means the envelope, cylindrical shape envelope, can be increased a lot compared to the other one.
Well, that's a point Lou made at the first as well, in terms of going up and down, since I have two linear movement. Actually, in this, I have a cube workspace, which are rotating that cube. Imagine a box, okay? Because going up and down, back and forth, creates a box shape area for you, all right? And this rotation moves that box around. So what you have is a workspace you're covering by these two joints, linear Cartesian joints, and that area is moved around by this rotation. In the other one, however, what do you have is kind of piece of cylinder, sorry, bad drawing, like this. You have this fixed, and the other one rotates that box around. So here, the end area, if you move only these two last joints, you will cover this. And with this joint, because this joint is same, you see, between this one and the other one, this joint is similar, R in both. But I have R, T, and the other one I have RTT. So the difference is, if I have this one fixed, I'll cover this area with minimal movement. Okay, it means this one is not moving, so this will cover that area. But in the other one, you will cover actually a cube volume or cube area, and with the rotation, like you are moving that. Well, that in many cases might not make any difference. Actually, we might not care about the geometry of the robot, do more care about the actuators and the force and the size and the manufacturer and many different things, because our tasks are not very complicated, but technically looking into details, we can make these discussions as well. So Jason says, doesn't speed depend on the mechanism driving? Yes, to drivers, exactly. And such a ball square, rotary gear, etc. You can make up it with gear ratio. Yeah, I agree. As I said, the force, if you just focus on the force or speed, you have to consider dynamic. Dynamic means mass and force. We have to talk about mass, force, and even time. So M, F, and T. Here, we are not considering those yet. We just look into geometry, just a structure. We are not considering anything else. But when it comes to speed, when it comes to force, when it comes to time, you have to include this as well. Some of them might have capability to be designed lighter. Some of them might have capability, to be designed with stronger actuators. Some of them might not. All right. So let me see what I have, and the other one is Cartesian. In the Cartesian form, you have TTT, means I have I have translational, move linear, and move linear. Okay, like this, like what you see here, So you have linear movement. The Cartesian arm has all three joints of the translational type, called TTT. The workspace is a person, is a cube or person, just basically depending on the shape, because you also know that your link need to be linear. Your link can be bended, can be shaped, different shapes depending on what you need. And actually, you need to shape your links as well, considering the mass and force you're applying at different. It doesn't make sense if I have all of them with the same size, same shape, but it depends on application and type of robot we are using. Okay. Robot wrist. when it comes to robot wrist is normally 3 degrees of freedom just in one case. Normally we have RRR, very similar, as I said, to our human wrist. You see, you have rotation in one direction. I hope you can see me. One rotation. Another rotation is not too much, but still we have another rotation like that, and another type of rotation like this. Okay, it's very similar to what we have in airplane position, like pitch yaw and yeah, in airplane, similar to that. In a robot hand, an effector as well. It can be grippers, different kind of end effectors, depending on what do you want to do. Gripper is the one which can grip or get something with robot, but not necessarily all the end effectors, all the ending of the arm are grippers. There can be different things to pick up using, magnetic, using vacuum, or just perforation, just going inside the hole and pick up something to move them and displacement in your manufacturing line. The gripper itself has a mechanism, mechanical design. Here in this class, we are not talking about mechanical design, but mechanical student should be able to design and discuss how to design a gripper. So, for example, what you see here is you have a greaser. I'm sorry, I talked too much. Sorry, that's why a gripper like this. So it's very similar to a scissor. That's why I made the mistake. So what you have, you're moving down this, and your gripper can, depending on the length and the force you're applying here can be different. Not just one type. You might have motor using and producing that force, and different kind of mechanism just for the gripper, just for the end effector to grip or to catch, to get a piece of material or an object in manufacturing line. So industrial robotics, briefly, we'll have a look at those. So if you agree, I think it's better to have a short break and then go and come back. Any question?
No.
Do you agree to have a short break? I think I have to. Lou says no. You don't want to break, Lou? Oh, no question. Okay. All right. In 2:15, okay?